So the Ka-case ratio is sort of like we already mentioned, and I think most of you already know that. Then the second subject we are going to talk today is the codon-based test, and most is by PEMO. So you will learn PEMO in one of our laboratory courses, and using PEMO as a software method to calculate or to estimate the top positive selection. That can also give you the estimates of DN and DS. And I put a website there so you can look up. So the PEMO was developed by Zihin Yang in UK. Then the paper, I think the recent paper, PEMO 4, is published a few years ago. Okay. So what do we mean by codon-based comparison? It means when we consider the evolution rate, we only look at each codon at a time. So in this figure, we can look at the codon differences. So from our multiple sequence alignment on the left of the slides, you can compare all the codons. And for each codon, you can estimate their differences. So from the multiple sequence alignment, you have a tree-based topology. So that's showing on the top. You have sequence 1, sequence 2, and sequence 3, and they diverge from a common ancestor. At this moment, we use one of the sequence as an outgroup. So this is a network. There's no root. And usually someone would think, oh, maybe the sequence 1 is more ancestral. But without further information, you cannot really do that. So usually, for example, if we use human and chimpanzee as a comparison and use mouse as an outgroup, although it's a very, very, very distant outgroup, but that's the sequence most available. And we can construct a phylogeny without any ambiguity because we all know chimp and human are much closer than a mouse. Then we can look at each codon down there. Then you can do the same thing as we practiced last time. You try to assign the changes on each branch. So now we can put, so in this example, you have TTT and TCC and TTC on each branch for each sequence. Then you can assign the changes on the branch A, B, or C. So that's totally based on the parsimony analysis. Then you do the same thing for synonymous and non-synonymous. So the computer will do that for you. Based on each codon, it will calculate the synonymous and non-synonymous sites, and also the changes. So the two things we did like previously. So they will do the same thing as well, then try to dissect the sequence into each branch. Then they use the maximum likelihood method. So I'm not going to go into the detail. So if you're interested, you probably need to take other courses to understand in more detail or look up the paper. But basically, they try to compute the parameters, given the parameters, and to look at the likelihood, use the likelihood ratio test between a possible alternatives. So we'll look at the possible alternatives. But because of their method, there are several things, the several parameters I want to remind you. Use kappa as the transition and transversion rate, and we mentioned about this in the previous lectures as well. And Zihan invent omega as the Ka-Ks or DN-DS ratio, and that is widely used now. So omega become a parameter indicate equal to dN over ds. Then the pi here is the equilibrium frequency of the codon. So that's like what estimate from the data. And you will have a set of parameters like this. So to look at the three sequences, we can separate the branches. So when we say branches, that means from on your right hand side of the slide, you will say the omega 1, omega 2, and omega 3. That's the KAKS ratio or DNDS ratio for each branch from the node in the middle. Then we want to test the alternative models. The model will come up a little bit later. And for each model, we'll estimate the likelihoods and use the ratio test, likelihood ratio test, to see which model is better than the other one. And that's based on the chi-square test. So the omega, it depends on like how the omega perform. So the omega could be like could follow the discrete gamma distribution, or it follows beta distribution. So there are two major assumptions, and for each one, they developed the likelihood ratio test. So I want to show you the models in his parameter. So this is the model test most we used. So a lot of times we test against, like let's say, against the two alternatives. And so if we base on the assumption of the gamma distribution, then we'll use the model 1A and 2A. So 1A is most neutral model, and that means based on the neutral hypothesis, and this will be the model estimates or your numbers or your estimates will be modeled by the neutral hypothesis. And the other one is the selection. So the selection, you can see down there, it will say the omega has different omega for each branch. So the differences between these two models are showing right here. So you say, well, if it's neutral, why you have an omega smaller than 1? So that's the idea showing in this model is most of the time for protein evolution, the Ka is always almost like a much smaller than the Ks. That's what commonly observed. So this is what's showing in this neutral model here. So actually this is the one have both neutral evolution, that's the omega equal to 1, and some negative selection in here. Then the alternative is the one with a specific branch which show greater omega value, also omega is greater than 1. So that's the major differences between the model 1 and model 2. And another will be follow the beta distribution assumption. That's the model 7 and 8. So the model 7 and 8 are similar to the previous one. One is based on sort of neutral, more neutral hypothesis. The other will based on a different distribution. So they both based on beta distribution, but test between the two hypotheses. So the ratio between the two will give us the significance, statistical significance of whether we reject the null hypothesis or whether we detect the positive selection, like along like each branch or among the branches we are testing. I just talked about the branch test. And another thing we could test in PEMO is the branch site test. So the branch site test, for branch test, each branch will calculate separately, but all the codons are averaged together. But think about the evolution at the molecular level. They are not really equal for each codon. It means some codon could have more flexibility to change to a different codon without or with little fitness consequence. But some of the codons are more important for the protein function. So if we average out, then if the important or the selection only acts on a few codons in a long stretch of sequences, and the signal will be eliminated. So in this case, it will be good to consider sites independently. So each codon we can look at and look at whether this site is significant, different than all the other sites. So we separate the branches and also look at each codon on each branch. So that's the idea of taking the branch site test. But some people also argue this will be too sensitive, or it will possibly give you a lot of false positives, and means a lot of those sites identified by the branch site test might not actually be the sites under positive selection. The argument we have here is the program is not to try to identify all the sites under positive selection. The program is to estimate the sites which possibly under positive selection. So to me, that's a list of suggestions for people who are really interested in the protein function. We can go ahead to design experiment and do a functional test. So there's a lot of discussions on how we can use PIML as a tool to identify sites under positive selection. There's also a number of papers against this idea, but I want you to just keep that in mind. This is something we do as an estimate, and they give us some suggestions. We are not going to use the results from the bench site test and say definitely those are the sites under positive selection and make the conclusion. So this is just like before you do all the tests, I want to understand a little bit more. So that's why some people still use the branch site test to estimate the possible codons under positive selection during evolutionary time. And this is like one of the examples on their model. So the parameters used the branch site model is similar to the others, but I want you to put more attention to like the omega value. So that's the one we try to estimate and try to compare between the models. And so when you want to use PIML, you have to be careful about which model are you compared to. So you're using one of the alternative models and do the likelihood ratio test. And we'll do a little bit more about this and during our laboratory courses.